What if everything we think we know about the universe is just the tip of the cosmic iceberg? Picture a spiral galaxy, its arms swirling gracefully through the void, stars tracing perfect orbits around its center, except they're not. According to the laws of physics as we understand them, those outer stars should be moving slower, flung outward by centrifugal force, but they're not. They're racing just as fast as the inner ones, defying gravity itself. For decades, scientists have explained this cosmic rebellion with one word: dark matter. An invisible, mysterious substance that outweighs everything we can see, bending the rules of the universe to its will. But here's the twist: we've never actually detected it. Not once. So what if dark matter isn't the answer? What if we've been staring at the cosmos through the wrong lens entirely? Today, we're diving into 26 unconventional theories that dare to challenge this decades-old dogma. From tweaked gravity to quantum quirks, from hidden dimensions to cosmic holograms, these ideas don't just question the status quo, they rip up the rulebook entirely. Some sound like science fiction, others are so elegant, so simple, they make you wonder why we ever looked elsewhere. But all of them share one thing: the audacity to imagine a universe where dark matter isn't the hero of the story. This isn't just about solving a puzzle, it's about rewriting the very fabric of reality. Because if even one of these theories is right, everything we thought we knew about galaxies, gravity, and the nature of existence itself could be up for grabs. So buckle up, we're about to take a journey through the wildest corners of astrophysics, where the answers might be hiding in plain sight, waiting for someone brave enough to see them. Ready to question everything? Let's begin. For nearly a century, dark matter has been the go-to explanation for one of the universe's most stubborn mysteries: why galaxies spin faster than they should. Picture a merry-go-round where the kids on the outer edge are somehow moving just as fast as those near the center, despite physics saying they should be flung off. That's exactly what happens in galaxies. The outer stars orbit just as quickly as the inner ones, defying Newton's laws, unless there's some invisible mass holding them in place. Enter dark matter, a cosmic placeholder, an unseen force that supposedly makes up over 85% of the universe's matter. It's the glue that keeps galaxies from flying apart, the hidden hand shaping the cosmos. But here's the catch: after decades of searching, we've never actually caught a single particle of it. Not with ultra-sensitive detectors buried deep underground, not with powerful particle colliders, not even with telescopes scanning the heavens for faint traces. Dark matter remains a ghost, a mathematical fix rather than a proven reality, and that sparked a quiet revolution in astrophysics. More scientists are asking, what if we've been chasing a shadow? The descent isn't just fringe speculation. Respected researchers point to gaps in the dark matter model, like the fact that some small galaxies rotate too smoothly, without the messy clumps dark matter should create. Others argue that the theory has become too flexible, adjusted and readjusted to fit every new observation, like a patchwork quilt with endless stitches but no real pattern. It's a bit like insisting an invisible elephant is rearranging your furniture every night, rather than questioning whether the floor might be uneven. And that's where the real fun begins, because if dark matter isn't the answer, what is? The first contender is as bold as it is controversial: a radical rethink of gravity itself. What if Newton and Einstein missed something fundamental? What if, on cosmic scales, gravity doesn't behave the way we've always assumed? This isn't just tinkering at the edges. It's tearing up the rulebook and starting from scratch. Enter modified Newtonian dynamics, or MOND, the boldest challenger to dark matter's throne. Proposed by physicist Mordechai Milgrom in the early 1980s, this theory flips the script entirely. Instead of invoking invisible matter, MOND suggests we've simply misunderstood gravity itself. At extremely low accelerations like those experienced by stars on the fringes of galaxies, Milgrom argued that Newton's laws might need a subtle tweak. Picture gravity as a rubber band. At everyday scales, it behaves predictably, but stretch it far enough, and it snaps into a different set of rules. MOND's elegance lies in its simplicity. Without a single dark matter particle, it accurately predicts the rotation curves of dozens of galaxies, matching observations with uncanny precision. Milgrom himself once quipped, "If you hear hoofbeats, think horses, not zebras." In other words, maybe the solution isn't an entire unseen universe, but a small adjustment to the physics we already know. Yet for all its triumphs, MOND stumbles when faced with the cosmic big leagues. When applied to galaxy clusters or the large-scale structure of the universe, its predictions start to wobble. The bullet cluster, for instance, a cosmic collision where visible matter and gravitational effects appear to separate, poses a thorny challenge. Dark matter models handle it neatly, while MOND requires creative fixes. Critics argue this makes it less a theory and more a galactic band-aid, brilliant in one context but fraying at the edges in others. Still, MOND persistence is a testament to its allure. It forces us to ask, are we clinging to dark matter because it's true, or because we've built too much on its shaky foundation? And if MOND isn't the final answer, could it be pointing toward something even stranger? Because waiting in the wings are theories that make modified gravity look tame, ideas that rewrite not just equations, but the very nature of reality. But what if gravity isn't even a fundamental force at all? That's the radical proposition behind emergent gravity, a theory that turns our understanding of the cosmos upside down. Dutch physicist Erik Verland threw a wrench into conventional physics when he suggested that gravity might not be one of the universe's basic building blocks, but something that emerges from a deeper, more mysterious layer of reality. Imagine walking into a movie theater and seeing shadows dancing on the screen. You might think the shadows themselves are the story, but they're really just a byproduct of the actual film playing behind the scenes. Verland argues gravity works the same way. It's not the main act, but a side effect of something far more profound: quantum entanglement. At the heart of this idea is the notion that space itself is built from countless tiny bits of quantum information, woven together like an unimaginably complex tapestry. When particles become entangled, linked in such a way that changing one instantly affects the other, no matter the distance, they create a hidden structure beneath spacetime. Verland's math suggests that gravity, as we experience it, is just the universe's way of keeping track of all these entangled connections. And here's the kicker: when you apply this framework to galaxies, their strange rotation curves suddenly make sense without invoking dark matter. The extra pull holding stars in place isn't coming from invisible stuff. It's embedded in the very fabric of how information organizes itself. Think of it like a crowd at a concert. From a distance, the movement of people looks smooth and predictable, as if guided by an unseen force. But up close, you see it's just individuals adjusting to each other, responding to subtle cues. Emergent gravity proposes that what we call dark matter effects are really just the collective behavior of quantum information, interacting in ways we're only beginning to decipher. Yet this theory isn't without its skeptics. Some argue that Verland's equations, while elegant, haven't yet been tested against the full complexity of the cosmos, like explaining the precise lensing effects seen in galaxy clusters. Others question whether emergent gravity can ever be more than a beautiful idea without direct experimental proof, but even critics admit it's a breathtaking leap. If gravity truly emerges from quantum entanglement, then the universe is far stranger and more interconnected than we ever imagined. And that's just the beginning, because if gravity can emerge from something deeper, what other fundamental forces might be illusions? Some theories take this even further, suggesting that spacetime itself is a hologram, or that our entire universe is a shadow of higher dimensional processes. The line between science and philosophy blurs, and the hunt for answers leads us down rabbit holes where the very nature of reality is up for grabs. What if one of the universe's most sacred constants isn't so constant after all? The speed of light, that unbreakable cosmic speed limit etched into the foundation of modern physics, might not have always been the same. This is the provocative idea behind variable speed of light theories, or VSL, a concept that could rewrite the rules of galactic rotation without a shred of dark matter. Imagine a universe where light itself was faster in its infancy, subtly altering the fabric of gravity over billions of years. Stars on the outskirts of galaxies wouldn't need invisible matter to explain their speed. Instead, the very equations governing their motion would change based on light's ancient behavior. The roots of this idea stretch back further than you might think. In the late 19th century, physicist Paul Dirac toyed with the notion that fundamental constants might evolve over time. But it wasn't until the 1990s that scientists like Joe Megiddo and John Barrow revived the concept with a twist. What if light speed was once radically different, leaving fingerprints in the way galaxies spin today? Their models suggest that in the early universe, light could have raced across space much faster, tweaking the strength of gravity in ways that now mimic dark matter's effects. It's like discovering that an old clock runs slow not because of hidden weights, but because the length of a second has changed. Here's where it gets even wilder. If light speed was variable, it wouldn't just affect galactic rotation, it could solve cosmic puzzles like the Horizon Problem, which asks why distant regions of the universe look so similar despite never having been in contact. Traditional inflation theory patches this with a rapid early expansion, but VSL offers an elegant alternative. If light traveled faster in the past, information could have spread across the cosmos before settling into today's steady pace. Yet VSL remains fiercely debated. Critics argue that altering the speed of light would send shockwaves through physics, destabilizing everything from quantum mechanics to nuclear reactions. Even a tiny change could rewrite the story of element formation in the early universe. Supporters counter that science has always progressed by questioning its assumptions. After all, Einstein himself shattered Newton's absolute time and space. The real sticking point, evidence. While some observations of distant quasars hint at possible variations in light speed, the data is far from conclusive. And that's the beauty of this debate. VSL doesn't just challenge dark matter, it forces us to ask which constants are truly fundamental and which might be relics of a deeper, unseen layer of reality. It's a reminder that even our most trusted rules might be provisional, waiting for the next bold mind to test their limits. Which brings us to the next frontier, theories that don't just tweak constants, but reshape Einstein's relativity itself. If light speed isn't sacred, what other pillars of physics might be ready to bend? What if the solution to dark matter's mystery isn't just tweaking gravity, but rebuilding it from the ground up? That's the ambitious goal of tensor vector scalar gravity, or TVS, a theory that takes MOND's rebellious spirit and grafts it onto Einstein's framework of relativity. Picture MOND as a daring sketch of a new physics, one that explains galaxy rotations beautifully but struggles to paint the full cosmic picture. TVS is that sketch refined into a masterpiece, adding layers of complexity to cover relativity's bases while preserving MOND core insight. At its heart, TVS introduces not one but three new fields to Einstein's equations: a tensor like gravity's traditional fabric, a vector, a directional push or pull, and a scalar, a universal background value that subtly adjusts gravity's strength. Together, they create a symphony of forces that mimic dark matter's effects without needing a single invisible particle. Think of it like a stage magician's trick. What looks like an extra hand tugging at the stars might just be gravity itself playing by different rules in the cosmic shadows. One of TVS's most striking predictions is how it handles light. In Einstein's relativity, gravity bends light along curved spacetime, but TVS suggests this bending could vary depending on the hidden scalar field, potentially explaining why galaxies lens light as if they contain more mass than we can see. It's a clever workaround, and for a while it seemed to bridge the gap between MOND galactic successes and the larger scale puzzles of cosmology. Yet even TVS has its skeptics. Some argue its equations are too convoluted, a Frankenstein's monster of physics. As one critic put it, pieced together to fit observations rather than emerging from first principles. Others point to collisions like the bullet cluster, where visible matter and gravitational effects separate cleanly, as a hurdle TVS still struggles to clear without borrowing ideas from dark matter. The theory's original architect, Jacob Bekenstein, acknowledged these challenges but saw them as growing pains for a radical new approach. What makes TVS fascinating isn't just its mechanics, it's the philosophical shift it represents. By weaving together relativity and modified dynamics, it dares to ask, could our entire understanding of gravity be incomplete, not just at the edges but at its core? And if so, might the answers lie not in hidden matter, but in the invisible scaffolding of spacetime itself? This brings us to the quantum realm, where gravity's rules blur into uncertainty. If TVS is a bridge between MOND and relativity, then quantum gravity theories are the uncharted territories beyond, where particles flicker in and out of existence, and the fabric of reality might be stitched together by strings or holograms. The journey from galactic rotations to quantum foam is a leap, but it's one that could rewrite the universe's deepest laws. The quantum vacuum isn't empty, it's a seething, bubbling ocean of energy, where particles flicker in and out of existence so fast they defy detection. This isn't science fiction, it's a bedrock principle of quantum mechanics, and it might hold the key to galactic rotation's greatest mystery. Imagine space itself as a frothing cosmic foam, where virtual particles, ghosts of matter and antimatter, constantly pop into being, collide, and vanish in fractions of a second. Normally, these fleeting bursts cancel each other out, leaving no trace. But what if, on the scale of galaxies, they don't? What if the quantum vacuum's restless energy exerts just enough push or pull to explain why stars on the outskirts of galaxies whirl faster than expected? This idea, known as quantum vacuum effects, suggests that dark matter's fingerprints might actually belong to spacetime itself. The math reveals something startling. The zero-point energy of the vacuum, the lowest possible energy state, where particles still jitter, could generate subtle gravitational anomalies. Picture a calm lake disturbed by countless tiny ripples. Individually, they're insignificant, but en masse, they could nudge a floating leaf in unexpected directions. Similarly, the quantum vacuum's ceaseless activity might bend spacetime ever so slightly, creating the illusion of invisible mass tugging at stars. Some theorists take this further, proposing that virtual particles could form fleeting clouds around galaxies, their collective gravity mimicking dark matter's pull. Others argue that the vacuum's energy density isn't uniform. It could vary across cosmic distances, creating pockets of stronger or weaker gravity. It's like blowing bubbles in a glass of soda. Some regions fizz more intensely, altering the fluid's overall behavior. But skepticism lingers. Critics point out that quantum vacuum energy is notoriously difficult to calculate. Its predicted strength often diverges wildly from observations, a problem known as the cosmological constant problem. If the vacuum's energy were as powerful as some equations suggest, the universe would have torn itself apart long ago. Yet supporters counter that we might be missing a crucial piece of the puzzle, a way the vacuum's energy screens itself on large scales, leaving only subtle traces in galactic dynamics. The real allure of this theory isn't just its potential to explain dark matter. It's the profound implication that the fabric of space isn't a passive stage but an active participant in the cosmos's dance. If quantum foam can influence galaxies, then emptiness is an illusion. Every cubic inch of the universe thrums with hidden activity, which raises an even wilder question. What if space isn't what we think it is at all? Beyond quantum foam lie theories that treat spacetime as an emergent hologram, a pixelated projection of deeper, stranger physics. The line between vacuum and matter blurs, and the hunt for dark matter's true nature becomes a journey into the heart of reality itself. What if galaxies aren't just islands in the cosmos, but part of an infinite cosmic tapestry, repeating the same patterns from the smallest quantum flutter to the grandest galactic swirl? This is the mind-bending premise of the fractal universe model, where the universe isn't just vast, it's recursive, echoing its own structure across every scale. Picture a snowflake's intricate branches mirrored in the branching arms of a spiral galaxy, or the way lightning's jagged bolts resemble the sprawling filaments of the cosmic web. If the cosmos truly operates this way, then the mystery of galaxy rotation might not need dark matter at all, just a fundamental rewrite of how we see space itself. The roots of this idea trace back to mathematician Benoit Mandelbrot, who revolutionized science by showing how chaos could hide breathtaking order. His work revealed that seemingly random shapes, coastlines, mountain ranges, even stock market fluctuations often follow fractal patterns, self-similar at any magnification. Apply this to cosmology, and the implications are staggering. If galaxies are fractal nodes in a grander pattern, their rotation could be governed by the geometry of the universe itself, not invisible mass. Imagine a river's current. The water flows faster where the channel narrows, not because of hidden forces, but because the shape of the riverbed dictates the motion. In a fractal cosmos, spacetime might have its own hidden geometry that nudges stars into unexpected orbits. Some theorists suggest this could explain why galaxy rotation curves defy Newtonian predictions. Instead of dark matter's gravitational pull, stars on the outskirts might be riding the flow of a fractal spacetime gradient, like leaves caught in the eddies of a vast, invisible whirlpool. Observations lend eerie support. The distribution of matter in the universe, from galaxy clusters down to interstellar dust, often follows fractal-like scaling laws. Even the voids between galaxies aren't truly empty. They're structured in ways that echo smaller scale patterns, yet the fractal model faces fierce debate. Critics argue that while the universe shows fractal-like features at certain scales, it smooths out over larger distances, a deal-breaker for a truly fractal cosmos. Others point out that without a clear mechanism linking fractal geometry to gravity's behavior, the theory remains more poetry than physics. But its boldest proponents counter that we've barely scratched the surface. If space-time is fractal, then our current laws of gravity might be like trying to describe a symphony using only the sound of a single violin, missing the harmony of the whole. And that harmony could be hiding in dimensions beyond our own. If fractal geometry hints at a deeper cosmic order, then hidden dimensions curled up like microscopic origami might hold the key. String theory's extra dimensions, for instance, could warp spacetime in ways that mimic fractal behavior on galactic scales. It's a dizzying thought. The universe's grandest mysteries might not be solved by adding more matter, but by realizing we've been missing entire layers of reality. The fractal model doesn't just challenge dark matter. It invites us to see the cosmos not as a collection of objects, but as a living pattern, endlessly repeating, infinitely connected. Which raises a haunting question. If the universe is fractal, are we, too, just patterns within patterns, echoes of something far greater? The answer might lie not in the stars, but in the spaces between them where geometry becomes gravity, and the fabric of reality folds back on itself. What if our universe is just a thin slice of reality, floating like a leaf on the surface of an unseen cosmic pond? This is the startling vision of brain world scenarios, where the three dimensions we know might be one small part of a far richer, higher dimensional existence. The name comes from membrane. Imagine our entire cosmos as a vast, flexible sheet adrift in a space with 4, 5, or even 10 dimensions. In this picture, gravity could behave differently than we expect, not because of dark matter, but because it's leaking into those hidden dimensions, weakening its grip on galactic scales while leaving other forces untouched. Here's how it could solve the rotation mystery. Normally, gravity weakens with distance. Drop a rock from twice as high, and it takes longer to hit the ground. But if gravity spills into extra dimensions, its strength might fade faster in our three-dimensional brain, making it seem like something invisible is helping hold galaxies together. Picture a flashlight shining through a curtain. From our side, the light appears dimmer, as if some brightness has vanished into the fabric. Similarly, gravity's apparent shortage in galaxies might just be the shadow of its true strength, radiating into dimensions we can't see. String theory fans will recognize this idea. In many string models, the universe's fundamental threads vibrate in higher dimensions, and our brain could be one of countless parallel realities stacked like pages in a book. Some versions even suggest that dark matter particles might be ordinary matter from a neighboring brain, invisibly tugging at our stars through shared gravity. It's a dizzying thought. The missing mass haunting our equations might literally exist in another plane of reality, separated from us by a dimensional veil. Yet brain worlds come with their own puzzles. If gravity leaks, why don't we see other effects, like tiny deviations in planetary orbits? And how do these extra dimensions stay curled up so tightly that we never notice them? Supporters argue that the scales involved are unimaginably small, dimensions folded far beyond our current power to probe. But critics counter that without testable predictions, the theory risks becoming pure speculation, elegant but untouchable. Which leads us to an even deeper question. What if the problem isn't gravity or dimensions, but mass itself? Could the very concept of matter need reimagining? Theories like negative mass or exotic fields suggest that the universe's ingredients might be far stranger than we've dared to assume. The search for answers doesn't end with hidden dimensions. It twists into new territory, where the building blocks of reality might not be blocks at all, but echoes of something more fluid, more elusive. What if the universe isn't just missing matter, it's hiding matter with negative mass? This isn't science fiction. It's a radical proposal that flips our understanding of physics on its head. Imagine a cosmic ingredient that doesn't just lack gravity, but actively repels it, stuff that falls up instead of down, accelerating away from normal matter like two magnets pushing apart. If such exotic particles exist, they could counterbalance dark matter's gravitational pull, explaining why galaxies spin faster without invoking invisible clumps. It's a twist so audacious, even Einstein only toyed with it briefly before dismissing it as ghostly. But today, physicists are resurrecting the idea, asking, what if the universe's missing piece isn't just hidden, it's fundamentally backwards? The math behind negative mass is stranger than fiction. Unlike antimatter, which behaves like ordinary matter but with opposite charge, negative mass would defy Newton's most basic laws. Push it, and instead of moving forward, it would accelerate backward, as if inertia itself reversed. Combine it with positive mass, and the pair would self-accelerate indefinitely, a phenomenon dubbed the runaway motion effect. At first glance, this sounds like a recipe for cosmic chaos, yet theorists argue these particles could stabilize galaxies in unexpected ways. Picture a cosmic tug of war. Dark matter pulls stars inward, while negative mass pushes outward, creating an equilibrium that matches observed rotations. Some models even suggest negative mass could form invisible halos around galaxies, their repulsive gravity perfectly offsetting the need for dark matter's extra pull. But the theory isn't without its ghosts. Critics point out that negative mass would violate energy conditions crucial to general relativity, potentially allowing time travel or perpetual motion machines physics' ultimate taboos. Others argue that if negative mass existed, we'd see evidence in the large-scale structure of the universe, like voids between galaxies expanding unnaturally fast. And then there's the elephant in the room. No one has ever detected a particle with negative mass, not even a hint. Supporters counter that absence of evidence isn't evidence of absence. After all, we once thought neutrinos were massless too. The real allure of negative mass lies in its sheer audacity. It doesn't just tweak equations, it forces us to question whether all matter must play by the same rules. If confirmed, it would rewrite not just galactic dynamics but the very meaning of mass, energy, and motion, which raises an even more provocative question. What if the missing variable isn't mass at all, but time? Theories like varying physical constants suggest that time's flow might not be uniform, subtly altering gravity's strength over cosmic epochs. Imagine a universe where clocks tick faster in some regions, slower in others, bending the rules of motion in ways that mimic dark matter's hand. The line between science and philosophy blurs, and the hunt for answers ventures into realms where time itself becomes fluid. What if gravity isn't a fixed law of nature, but a force that ebbs and flows with the age of the universe? This is the core idea behind time-varying gravity, a theory that dares to suggest the strength of gravity might not be constant over cosmic timescales. Picture a river whose current grows weaker as the centuries pass, subtly altering how leaves drift on its surface. Now imagine that river is gravity itself, and the leaves are galaxies, their rotation curves shaped not by dark matter, but by the slow, imperceptible fading of gravity's grip. The roots of this idea stretch back to physicist Paul Dirac's large numbers hypothesis. A curious observation from the 1930s, Dirac noticed something eerie. The ratio of the universe's size to the size of a proton is roughly the same as the ratio of the gravitational force to the electric force inside atoms, about 40 orders of magnitude. Coincidence? Dirac thought not. He proposed these ratios might be linked, hinting that fundamental constants, including gravity, could evolve as the universe expands. It's as if the universe's rulebook isn't written in permanent ink, but in pencil, with values that adjust as cosmic epochs pass. Fast forward to today, and time-varying gravity has resurfaced as a dark matter alternative. If gravity was stronger in the early universe, it could have imprinted itself onto galaxy formation, leaving behind rotation curves that appear to need dark matter, when in reality, they're fossils of a bygone era when gravity played by different rules. Think of it like an old vinyl record. The music sounds a certain way not because of hidden instruments, but because the needle's speed has changed over time. Similarly, galaxies might spin faster not because of invisible mass, but because gravity's volume was turned up higher when they formed. But how would this work in practice? Some models suggest gravity's strength could be tied to the universe's expansion rate, weakening as space stretches, like a rubber band losing its snap. Others propose that gravity leaks into extra dimensions over time, diluting its effect in our visible reality. The most tantalizing versions blend time-varying gravity with other unconventional ideas, like MOND or quantum vacuum effects, creating hybrid theories where multiple radical mechanisms work in concert. Imagine a cosmic orchestra where gravity's instruments aren't just playing different notes, they're retuning themselves mid-performance. Critics, of course, raise sharp questions. If gravity changes over time, why don't we see its effects in ancient star clusters or planetary orbits? Supporters counter that the shifts might be too subtle to detect locally, only becoming obvious across galactic scales. And there's the thorny issue of energy conservation. Would varying gravity violate one of physics' most sacred principles? Some theorists argue no, proposing that gravity's lost strength might transform into other forms of energy, like dark radiation or space-time curvature. What makes this theory so compelling isn't just its potential to solve the dark matter puzzle, it's the philosophical shift it demands. If gravity varies, then the laws we consider universal might be anything but. The constants we rely on could be cosmic variables, their values locked to the universe's age like hands on a clock. And if that's true for gravity, what about light speed or the charge of an electron? The door cracks open to a universe far more fluid, more dynamic than we ever imagined, which leads us to the next frontier, theories that refuse to pick just one radical idea, but instead weave them together into a tapestry even bolder than the sum of its parts. Because if the universe is this mysterious, why limit ourselves to a single explanation? The answer might lie not in choosing between modified gravity, quantum foam, or extra dimensions, but in realizing they could all be pieces of the same puzzle. What if the solution to dark matter's mystery isn't choosing between modified gravity and relativity, but merging them into something entirely new? Enter hybrid MOND relativity models, the boldest attempt yet to bridge the gap between Milgrom's revolutionary idea and Einstein's enduring masterpiece. Picture trying to build a bridge between two islands separated by a chasm. On one side, MOND uncanny accuracy at galactic scales. On the other, relativity's flawless track record with black holes and the cosmos at large. Hybrid theories are the architects daring to span that divide, stitching together equations that might finally explain everything without dark matter's shadowy crutch. At the heart of these models lies a delicate balancing act. Traditional MOND tweaks Newton's laws to fit galaxy rotations but stumbles when faced with relativity's domain, like the precise bending of light around massive objects. Relativity, meanwhile, handles cosmic-scale gravity beautifully but needs dark matter as a patch for galactic oddities. Hybrid theories propose a middle path, gravity that behaves like MOND in the weak field regime of galaxies but reverts to Einstein's rules where relativity dominates. Think of it as a cosmic traffic system where gravity changes lanes depending on the road conditions, slowing down to MOND speed limit in galactic suburbs, but accelerating back to relativity's rules on the cosmic highway. One standout approach is relativistic MOND, a framework where Milgrom's modifications are baked into relativity's equations from the start. Instead of treating MOND as an add-on, these models treat it as a fundamental feature of spacetime itself, like a hidden switch that flips gravity's behavior at certain thresholds. Recent simulations show promise. Some hybrid versions can almost replicate the bullet cluster's gravitational lensing without dark matter, a feat pure MOND could never manage. The key innovation, allowing spacetime's curvature to respond differently to the ultra-weak gravitational fields at galaxy edges, creating effects that mimic invisible mass. Yet the challenges are as stark as the ambitions. Hybrid models often require exotic fields or finely tuned parameters to work, leading critics to argue they're just dark matter in disguise, replacing one mystery with another. Others point out that these theories struggle to explain the cosmic microwave background's precise patterns, which dark matter handles effortlessly. Even proponents admit the math can feel clunky, like forcing two brilliant but stubborn musicians to play the same symphony in different keys. But the quest is far from over. Cutting-edge research is exploring whether quantum effects or hidden symmetries could smooth out the rough edges. Some theorists are even weaving in ideas from plasma physics, where charged particles in space might generate large-scale electromagnetic fields that subtly alter galactic dynamics. Imagine the universe not as a sea of invisible matter, but as a vast, crackling circuit where currents of ionized gas twist gravity's arm in ways we're only beginning to map. This fusion of disciplines hints at something profound. The answer to dark matter's riddle might not live in any single theory, but in the uncharted spaces between them. As hybrid models evolve, they're not just testing gravity, they're redefining what a complete theory of the cosmos could even look like. And that journey, however messy, might be the only way to glimpse the universe's truest face. Now consider this: if spacetime itself can shift its rules based on context, what other constants might be playing by hidden variables? The next frontier doesn't just tweak gravity, it questions whether our entire understanding of mass and energy is built on illusions. And the clues might lie not in the void, but in the electrified storms of cosmic plasma. What if we've been searching for dark matter in all the wrong places, not in ghostly particles or tweaked gravity, but in the electrified storms raging between the stars? Plasma cosmology dares to flip the script entirely, suggesting that the force shaping galaxies isn't gravity alone, but the invisible hand of electromagnetism. Picture the cosmos not as a static sea of matter, but as a living circuit crackling with currents of ionized gas so vast they could wrap around galaxies like cosmic spiderwebs. These aren't just abstract ideas. Plasma fills 99% of the visible universe, and its behavior might hold the key to why stars on the fringes of galaxies defy expectations. The roots of this theory stretch back to the visionary work of physicist Hans Alfvén, who won a Nobel Prize for revealing how plasma's superheated soups of charged particles can generate powerful electromagnetic fields when they move. On Earth, we see this in solar flares or the shimmering auroras, but scale it up to galactic proportions, and Alfvén argued these currents could sculpt entire galaxies, their magnetic fields whipping stars into faster orbits like marbles spun around a magnet. Imagine a galaxy not as an island of stars held together by gravity's glue, but as a dynamo, its rotation powered by invisible filaments of electrified plasma threading through space. Mainstream cosmology dismisses this as fringe. After all, gravity dominates on cosmic scales, and plasmas are notoriously messy to model. But plasma proponents point to eerie cosmic structures like Birkeland currents, twisted ropes of magnetic energy that stretch across light years, or the vast, empty voids between galaxies that might not be empty at all, just threaded with faint, galaxy-spanning currents too diffuse to see. Even the Milky Way's own magnetic field, discovered to be far stronger than expected, hints that electromagnetism's role might be chronically underestimated. Critics counter that plasma forces weaken over distance, making them unlikely to replace dark matter's galaxy-wide grip. Yet simulations show that under the right conditions, plasma instabilities could create large-scale structures mimicking dark matter's effects, like cosmic mirages where magnetism masquerades as mass. It's a radical proposition. The missing piece of the puzzle might not be matter or gravity, but the universe's own hidden electrical wiring. Which leads us to an even deeper mystery. What if the voids between galaxies aren't just blank spaces, but active players in this cosmic drama? Theories of inhomogeneous cosmology suggest these vast, seemingly empty regions might warp the fabric of spacetime itself, subtly altering how galaxies rotate from the outside in. Imagine a galaxy floating in a bubble of distorted gravity, its stars tugged not by invisible matter within, but by the emptiness stretching beyond. The universe, it seems, is full of ghosts, not just the ones we've invented, but the ones we've overlooked. What if the secret to galaxy rotation isn't hidden in the stars, but in the vast cosmic deserts between them? Void-based explanations turn our gaze away from clusters and galaxies, focusing instead on the immense, nearly empty regions that stretch across the universe like silent giants. These voids aren't just blank spaces, they might be warping gravity itself, sculpting the motion of galaxies in ways we're only beginning to grasp. Picture a ship sailing across the ocean. Its path isn't just shaped by the water beneath it, but by the distant pull of unseen trenches and currents. Similarly, galaxies might be swayed not by invisible matter within them, but by the gravitational shadows cast by the voids surrounding them. The math behind this idea is as elegant as it is radical. Einstein's relativity tells us that massive objects curve spacetime, but what happens when that object is a colossal absence of matter? Voids, some spanning hundreds of millions of light years, exert a kind of anti-gravity effect. Their emptiness creates a gravitational hill, pushing galaxies away rather than pulling them in. Stars on the outskirts of a galaxy, perched near the edge of this cosmic hill, might feel an extra nudge outward, mimicking the effect of dark matter's pull without needing a single particle of it. It's like rolling marbles on a stretched rubber sheet. A depression like a galaxy cluster tugs objects inward, but a raised region like a void can send them rolling faster, as if an unseen hand were helping them along. Observational hints of this phenomenon are already cropping up. Surveys like the Sloan Digital Sky Survey have mapped thousands of voids, revealing that galaxies near their edges often move in peculiar ways. Some exhibit flows that can't be explained by visible matter alone, while others spin faster than expected, exactly what void-based models predict. Even the cosmic microwave background, the afterglow of the Big Bang, shows subtle temperature dips around voids, as if the universe itself remembers their gravitational imprint. Yet critics aren't convinced. If voids are the puppeteers behind galaxy rotation, why don't all galaxies near voids show the same anomalies? And how do these models explain the bullet cluster, where gravity's effects seem divorced from visible matter entirely? Supporters counter that voids might be just one piece of the puzzle, a cosmic accomplice rather than the sole culprit. Their influence could combine with other factors, like modified gravity or quantum vacuum effects, in a grand interplay we're only starting to decode. This leads us to an even deeper question. What if inertia, the tendency of objects to resist changes in motion, isn't a fundamental property, but something shaped by the universe's hidden architecture? Theories like Mach's principle, once dismissed as philosophical musing, are making a comeback. Einstein himself toyed with the idea that inertia might arise from the combined gravitational influence of all matter in the cosmos. In other words, a star's resistance to slowing down could be due to the distant tug of galaxies and voids billions of light years away. It's a dizzying thought. The spin of a single galaxy might be choreographed by the entire universe. Imagine inertia as the hum of a cosmic symphony, where every particle's motion is a note shaped by the collective presence of everything else. If true, then dark matter's ghostly pull might not be missing at all. It could be the universe's way of whispering to its parts, urging them to move in harmony. The line between local and global blurs, and the answer to galaxy rotation might lie not in the stars, but in the silent spaces between them where the void speaks louder than we ever imagined. What if the spin of every galaxy is secretly choreographed by the entire cosmos? This is the essence of Mach's principle, a century-old idea that's staging a dramatic comeback in the dark matter debate. Picture a child spinning in a vast, empty playground. According to Newton, their dizziness comes from resisting absolute space. But Ernst Mach, the physicist who inspired Einstein, argued otherwise. That child's spin only has meaning because of the distant stars. Their combined mass stretching across the universe defines what it means to rotate at all. Take those stars away, and the very concept of spinning loses its meaning. Now apply this to galaxies. If inertia, the resistance to changes in motion, isn't an intrinsic property but a cosmic conversation between every particle in the universe, then the way stars whirl at galaxy edges might not need dark matter to explain it. Instead, their motion could be sculpted by the gravitational whispers of trillions of distant galaxies, a subtle tug of war woven into the fabric of space-time itself. Modern physics is giving Mach's idea new life. Some theorists argue that if the universe's total mass distribution influences local inertia, then galaxies floating near vast cosmic voids, regions with far fewer neighboring galaxies, might experience weakened inertial effects. Stars on their outskirts could behave as if they're lighter, requiring less centrifugal force to maintain their orbits. It's like a figure skater spinning effortlessly in an empty rink, her motion unchallenged by the usual friction of a crowd. This could mimic dark matter's gravitational boost without invoking unseen particles. Even Einstein flirted with this notion, weaving Machian ideas into his early relativity drafts before reluctantly dropping them as too radical. Now, advanced simulations are testing whether Mach's principle, combined with general relativity, might reproduce galactic rotation curves purely through the gravitational imprint of the universe's large-scale structure. Yet Mach's principle remains contentious. Critics argue it's too vague to test how exactly does distant matter communicate its influence instantaneously across billions of light years. Supporters counter that quantum entanglement already shows particles influencing each other faster than light, so why not inertia? Others propose hybrid models where Mach's cosmic inertia works in tandem with modified gravity, creating a feedback loop between local dynamics and the universe's grand architecture. It's a dizzying thought. The spin of a single star might be a vote in a cosmic referendum, its motion tallying the gravitational pull of everything that exists. This cosmic interconnectedness leads us to an even wilder frontier: dark energy's potential role in the inertia puzzle. If the universe's accelerating expansion is stretching spacetime itself, could that stretching subtly alter how inertia manifests on galactic scales? Some theories suggest dark energy's repulsive force might screen the gravitational influence of distant matter, weakening Machian effects in unexpected ways. Imagine inertia as a rubber band stretched by the cosmos's expansion. The farther apart galaxies drift, the less they feel each other's tug, potentially tweaking rotation curves in ways we're only starting to model. Whether Mach was right or not, his principle forces us to confront a profound truth. Nothing in the universe moves in isolation. From the spin of a galaxy to the curl of a galaxy cluster, motion might be a collective phenomenon, written in the gravitational handwriting of everything that ever was. And that handwriting could hold the key to dark matter's greatest riddle, not as a missing substance, but as a cosmic conversation we're only beginning to overhear. What if dark energy, the mysterious force accelerating the universe's expansion, isn't just pushing galaxies apart but actively warping gravity itself? This is the daring premise behind dark energy-gravity coupling, a theory that suggests the universe's two greatest enigmas might be locked in a cosmic tug-of-war. Picture dark matter as the anchor, its gravity holding galaxies together, while dark energy plays the rebel, stretching space-time with its repulsive force. Now imagine these two giants aren't fighting independently but are entangled in a delicate dance, their opposing forces bending the rules of motion in ways that could explain galactic rotation without needing dark matter at all. Recent theoretical work reveals how this might unfold. Some models propose that dark energy's influence isn't uniform. It could vary across space, creating regions where its push subtly counteracts gravity's pull. In galactic outskirts, where gravity weakens, dark energy's repulsion might dominate just enough to mimic the extra tug we attribute to dark matter. Think of it like a game of cosmic seesaw. As stars orbit farther from a galaxy's center, dark energy's upward nudge offsets the expected drop in rotational speed, keeping outer stars whirling as fast as inner ones. The math is still in its infancy, but early simulations show tantalizing hints that this balancing act could reproduce observed rotation curves. Critics argue the idea is speculative after all. We understand even less about dark energy than dark matter. Yet supporters point to anomalies in galaxy cluster dynamics, where gravitational lensing effects sometimes deviate from dark matter predictions in ways that align with dark energy's proposed interference. It's as if the universe left breadcrumbs and we're only now learning to read them. This interplay between cosmic forces leads us to an unexpected parallel: condensed matter physics. Just as electrons in a crystal lattice can exhibit collective behavior that defies individual particle rules, space-time itself might harbor emergent properties where dark energy and gravity interact in ways neither could alone. Some theorists are borrowing tools from superconductivity research, where paired electrons move without resistance, to model how dark energy might screen gravity on galactic scales. The universe, it seems, delights in echoing its patterns across vastly different domains. The implications are staggering. If dark energy and gravity are entwined, then solving galactic rotation might require rewriting our understanding of both. The cosmos refuses to be siloed. Its greatest mysteries are conversations, not monologues, and that conversation might just rewrite the laws of physics as we know them. What if space-time isn't just an empty stage but a cosmic superfluid flowing, frictionless, and capable of behaviors so bizarre they defy classical physics? Superfluid vacuum theory proposes exactly this, that the fabric of the universe might behave like an ultra-cold quantum liquid, one where gravity's quirks emerge from the swirling currents of space-time itself. Picture a river of helium cooled to near absolute zero, where vortices form without resistance and waves propagate endlessly. Now imagine space-time as that river, its subtle undulations not just carrying galaxies but actively shaping their motion. In this view, the extra pull we attribute to dark matter could be a side effect of spacetime's superfluid dynamics, like whirlpools in a cosmic bath, tugging stars along unexpected paths. The math behind this idea is as elegant as it is radical. In superfluid helium, quantized vortices, tiny tornadoes of swirling fluid, form when rotation exceeds a critical threshold. Apply this to space-time, and galactic rotation curves might simply reflect the universe's natural flow rate, with outer stars riding superfluid vortices that mimic dark matter's gravitational grip. Some models even suggest that spacetime's superfluid properties could resolve the cosmological constant problem, explaining why vacuum energy doesn't rip the universe apart. It's a tantalizing two-for-one. Dark matter and dark energy might both be illusions, emergent from the quantum turbulence of spacetime's hidden fluidity. Yet proving this theory is like trying to measure the ripples in a glass of water while floating in the middle of the ocean. The predicted effects are vanishingly small on human scales, and no experiment has yet detected spacetime's supposed superfluid properties directly. Critics argue it's a beautiful metaphor without empirical teeth until we can tap spacetime like a barrel of liquid helium. The theory remains in the realm of speculation. But supporters counter that indirect evidence might lie in anomalies like gravitational wave echoes or the way certain quantum particles interact with vacuum fluctuations. The hunt is on for cosmic signatures that could betray spacetime's liquid secrets. This fluid perspective leads us to an even more dramatic possibility. What if spacetime's behavior isn't just superfluid, but echoes the strangest objects in the cosmos, black holes? Theories like the dark matter as primordial black holes hypothesis suggest that the missing mass could be countless ancient black holes forged in the universe's first seconds. Others propose that black holes' event horizons might generate emergent gravity effects similar to superfluid vortices, warping spacetime in ways that cascade across galactic scales. The line between vacuum and singularity blurs, and the answers to dark matter's riddle might lie not in particles or fields, but in the way spacetime itself fractures under extreme conditions. Imagine a universe where gravity's rules are written not in the language of particles, but in the swirls and eddies of an invisible quantum sea. The superfluid vacuum theory doesn't just challenge dark matter. It invites us to rethink whether spacetime is a passive backdrop or an active, churning participant in the cosmic dance. And if it's the latter, then every galaxy's spin might be less a product of hidden mass and more a fingerprint of the universe's deepest, most fluid rhythms. What if dark matter isn't made of exotic particles at all, but of black holes so ancient they predate the first stars? This is the spine-tingling premise behind primordial black hole halos, a theory that dares to suggest the universe's missing mass could be hiding in plain sight, woven into the fabric of reality since the dawn of time. Picture the cosmos in its infancy, a seething cauldron of energy just moments after the Big Bang. In that chaos, tiny fluctuations in density might have collapsed directly into black holes, some no heavier than an asteroid, others as massive as 1,000 suns. Billions of these relics could still lurk undetected, drifting through galaxies like invisible ghosts, their collective gravity mimicking the effects we attribute to dark matter. The beauty of this idea lies in its simplicity. Unlike hypothetical dark matter particles, which require new physics to explain their existence, primordial black holes are built from gravity alone, a force we already know. They wouldn't need to interact with light or matter. Their sheer mass would bend spacetime enough to explain why galaxies rotate too fast. Imagine a swarm of bees too small to see, but whose combined buzz shakes the leaves on a tree. Similarly, these black holes could be the unseen architects of galactic motion, their gravitational hum guiding stars into unexpected orbits. But how do you hunt for something that emits no light and could be smaller than an atom? Astronomers have turned to ingenious methods. Some search for microlensing events, brief flashes when a primordial black hole passes in front of a distant star, warping its light like a cosmic magnifying glass. Others scrutinize the cosmic microwave background for telltale ripples left by black holes in the universe's first moments. Even gravitational wave detectors like LIGO might catch collisions between these ancient objects, their mergers sending tremors through spacetime. So far, the evidence is tantalizing but thin. A handful of unexplained microlensing events and peculiar gravitational wave signals could be hints or just cosmic noise. Critics argue that primordial black holes face a Goldilocks problem. Too many small ones would have evaporated by now, thanks to Hawking radiation. Too many large ones would disrupt star clusters or gobble up neutron stars, leaving scars we don't observe. The sweet spot, black holes around 30 times the mass of the Sun, isn't ruled out, but it's a narrow window to explain all of dark matter. Yet supporters counter that the universe is vast and our searches are still in their infancy. If these black holes are rare, clumped, or hiding in galactic halos, we might have barely scratched the surface. This cosmic hide-and-seek leads to an even deeper question. Could black holes be more than just gravity traps? Theories like the holographic principle suggest that black holes might encode information on their surfaces, like a cosmic hard drive. If true, then the universe's missing mass could be tied to the way information itself structures reality, a notion that blurs the line between physics and philosophy. Imagine a galaxy's rotation not as a problem of matter, but of data. The motions we observe might be the universe's way of processing information, with black holes as the invisible nodes in a vast computational network. From the quantum foam of the vacuum to the event horizons of primordial black holes, the hunt for dark matter keeps pushing us toward one unsettling truth. The universe's secrets might not live in the particles we can detect, but in the hidden architectures of spacetime and information. And that realization doesn't just challenge dark matter, it redefines what matter even means. What if our three-dimensional universe is just a shadow cast by a deeper, stranger reality? This is the mind-bending core of the holographic principle, the idea that all the information in our cosmos might be encoded on a two-dimensional surface at its edge, like a cosmic projector screen. Physicist Leonard Susskind, one of the theory's pioneers, likened it to a bank hologram. Scratch the shiny surface, and you'll find flat ridges containing all the data needed to reconstruct a 3D image. Now imagine that principle scaled up to galactic proportions. The way stars whirl at galaxy edges might not reflect hidden matter, but the way gravity itself emerges from this fundamental information layer, a cosmic glitch in the projection. The holographic principle turns conventional physics inside out. Normally, we think of gravity as a force sculpted by mass, warping spacetime like a bowling ball on a trampoline. But in a holographic universe, gravity could be an illusion, a side effect of how quantum information interacts on that distant 2D boundary. Picture a video game where every character's movement is determined by code written on the disk's surface, not by physics inside the game world. Similarly, a galaxy's rotation might not be driven by local gravity or dark matter, but by information processing happening at the universe's edge, billions of light years away. Susskind's work reveals how this could solve the dark matter puzzle. If gravity is emergent rather than fundamental, its strength might vary in ways that mimic invisible mass. Stars on galactic fringes could behave as if they're tugged by unseen matter, when in reality, they're responding to shifts in the universe's underlying information architecture. Think of it like pixels on a screen. Their behavior isn't governed by individual lights, but by the software controlling them. Some models even suggest that dark matter's gravitational effects could be artifacts of this cosmic coding, an information-theoretic glitch that makes galaxies appear heavier than they are. Yet the holographic principle isn't without its paradoxes. If our 3D world is a projection, Why does it feel so tangible? And how does information from the boundary translate into the precise gravitational forces we observe? Critics argue that until we can detect this cosmic hard drive directly, the theory remains speculative. But supporters point to surprising connections with black hole physics, where a hole's entropy, a measure of its information content, seems tied to its surface area, not its volume. It's as if nature itself hints that reality might be skin deep. This radical perspective leads us to an even more profound question. What if inertia, the tendency of objects to resist changes in motion, isn't intrinsic but holographic too? Modified inertia theories propose that an object's resistance to acceleration might depend on the universe's total mass distribution, as if every particle is subtly anchored to the cosmos's informational fabric. Imagine a galaxy's stars as buoys bobbing on a quantum ocean, their motion shaped not just by local forces but by the sea's unseen currents. The holographic principle doesn't just challenge dark matter. It invites us to wonder whether the universe's deepest laws are written in gravity, information, or something stranger still. From black holes to galactic spins, the answers might not lie in what we can see, but in the hidden codes of reality itself. And that realization doesn't just reshape our understanding of dark matter, it redefines what it means to exist in this universe at all. What if inertia, the stubborn resistance of objects to changes in motion, isn't a fundamental property, but a cosmic illusion sculpted by the universe's hidden glow? Quantized inertia, a theory pioneered by physicist Mike McCulloch, makes this jaw-dropping claim by tying inertia to an obscure quantum phenomenon called UNRA radiation. Picture a spaceship coasting through empty space. According to classical physics, pushing the ship requires energy to overcome its inertia. But McCulloch's math suggests this resistance isn't innate. It emerges from the ship's interaction with a ghostly sea of radiation that only appears when the ship accelerates. As the ship speeds up, the surrounding vacuum seemingly heats up, creating a thermal glow of UNRA radiation that pushes back against the motion. Now, scale this up to galactic proportions. Stars orbiting at the edges of galaxies experience such low accelerations that UNRA radiation becomes undetectably faint, altering their effective inertia in ways that mimic dark matter's gravitational grip. Suddenly, galaxies rotate too fast not because of invisible mass, but because the very rules of motion change at cosmic scales. The elegance of quantized inertia lies in its economy. It explains galactic rotation curves without inventing new particles or tweaking gravity. McCulloch's equations show eerie agreement with observed galaxy spins, matching data as precisely as dark matter models in some cases. Even more provocatively, the theory predicts anomalies in spacecraft trajectories, like the unexplained Pioneer anomaly, where NASA probes slowed slightly more than expected as they drifted toward the solar system's edge. Quantized inertia treats these as natural consequences of UNRA radiation's subtle drag, a cosmic friction we've overlooked, yet the theory faces fierce skepticism. Critics argue that UNRA radiation is notoriously weak, far too feeble to influence something as massive as a star. Others point out that McCulloch's equations rely on controversial assumptions about how wavelengths quantize at cosmic scales, a premise mainstream physics hasn't embraced. The biggest hurdle: no experiment has ever directly detected UNRA radiation, leaving quantized inertia resting on theoretical quicksand. Even supporters admit the math needs refinement to explain phenomena like the bullet cluster, where gravity's effects visibly separate from visible matter. But McCulloch's audacity forces a profound question. What if inertia isn't a law but a symptom, a cosmic side effect of deeper quantum processes? This idea doesn't just challenge dark matter, it reimagines motion itself as a conversation between objects and the universe's hidden energy fields. Which brings us to an even more exotic possibility: cosmic strings. These hypothetical cracks in space-time, thinner than an atom but stretching across the universe, could warp gravity in ways that mimic dark matter's pull. Imagine space-time as a frozen lake. Cosmic strings are the hairline fractures where the ice has split, creating tension that subtly alters everything nearby. If these strings exist, their gravitational shadows might nudge stars into faster orbits. No dark matter required. The universe's greatest mystery might not be missing matter, but invisible scars woven into the fabric of reality itself. What if the universe is threaded with invisible cracks, defects in spacetime, so thin they're almost one-dimensional, yet powerful enough to bend the fate of entire galaxies? This is the bizarre promise of cosmic strings, hypothetical relics from the universe's fiery infancy that could be twisting gravity itself. Picture the cosmos just after the Big Bang, a seething plasma cooling rapidly as it expands. Like ice forming on a pond, this phase transition might have left behind fractures, cosmic strings, where spacetime itself is pinched into unimaginably dense filaments thinner than a proton but stretching across billions of light years. These aren't just theoretical oddities. Their gravitational shadows could tug at stars with enough force to explain galaxy rotation curves. No dark matter required. The math behind cosmic strings is as elegant as it is strange. Unlike black holes which warp spacetime into spherical pits, strings create razor-sharp gravitational ridges. Think of a knife slicing through rubber sheeting, leaving a permanent crease. Anything passing near these creases would feel a sideways pull, as if space itself were tilted. Now imagine a galaxy laced with such strings. Stars orbiting near them would gain extra speed, as if pushed by invisible hands. Some models suggest that string networks could even form vast, invisible webs around galaxies, their combined gravity mimicking dark matter's halo effect. It's a cosmic illusion where spacetime's flaws masquerade as mass. Hunting these strings requires ingenuity. Since they emit no light, astronomers look for their gravitational fingerprint, like double images of distant quasars split by string-induced lensing, or abrupt jumps in the cosmic microwave background where a string's gravity shifts the afterglow of the Big Bang. Even more dramatic, if a string vibrates or snaps, it could send ripples through spacetime detectable as bursts of gravitational waves. The challenge. Strings are so thin that even one crossing our solar system might be missed unless it slices precisely through a planet, leaving a telltale scar in the rock record. Yet cosmic strings face skepticism. If they're so common, why haven't we seen clearer evidence? Some argue that strings would have decayed long ago, radiating away their energy. Others counter that certain string types could persist, woven into the universe's fabric like eternal threads. The debate hinges on a deeper question: did the early universe cool smoothly, or in a way that left behind these spacetime scars? This leads us to an even more radical frontier: theories where energy itself isn't conserved. In most physics, energy is sacred. It can't be created or destroyed, only transformed. But what if that rule isn't absolute? Some models suggest that in the presence of cosmic strings or other extreme spacetime defects, energy might leak into hidden dimensions or dissolve into the vacuum. Imagine a car losing speed without friction, seemingly defying physics, because its kinetic energy is secretly tunneling into another reality. Similarly, a star's motion might not balance neatly if spacetime's cracks siphon off gravitational energy. The implications are staggering. If energy isn't always conserved, then the equations we use to model galaxies and the universe might need rewriting. Cosmic strings don't just offer an alternative to dark matter. They challenge the bedrock principles we use to interpret the cosmos. And that realization doesn't just open new explanations, it forces us to ask which laws are truly universal, and which might be local quirks of a reality far stranger than we dreamed. What if the universe keeps its books a little fuzzier than we thought? Non-conservative gravity dares to challenge one of physics' most sacred principles, the unwavering conservation of energy. For centuries, we've treated energy like cosmic currency. It can change forms, but the total must always balance. Yet some theorists argue this accounting might break down at galactic scales, where gravity's grip could be subtly leaking energy into the void. Imagine a bank where money occasionally vanishes from vaults without explanation. Now picture that happening to the fabric of space-time itself, with gravitational energy dissipating in ways that alter how stars orbit. This isn't just bookkeeping, it's a revolution that could rewrite the rules of galactic motion without dark matter. The roots of this idea trace back to physicist Hermann Bondi's work in the 1950s, where he toyed with gravity models allowing energy to fade over cosmic distances. Modern versions suggest that in regions of extremely weak gravity like galaxy outskirts, spacetime itself might act like a sieve, letting gravitational energy trickle away. Stars orbiting there would behave as if an invisible hand were nudging them, maintaining their speed despite the expected drop-off. It's as if the universe has a hidden tax on gravity, skimming just enough energy to keep galaxies spinning smoothly. Some models even tie this to quantum vacuum effects, where energy fluctuates unpredictably at microscopic scales, potentially cascading into macroscopic anomalies. Critics bristle at the implications. If energy isn't conserved, what stops the universe from unraveling entirely? Supporters counter that the effect could be vanishingly small outside galactic halos, like a car's speedometer drifting slightly over decades, unnoticeable in daily driving but critical for interstellar navigation. Others propose that lost energy might not vanish but transform into something outside our current physics, like dark radiation or space-time curvature. The most radical interpretations suggest energy conservation might be a local phenomenon, not a universal law, a startling reminder that our physics was forged in a tiny corner of an unimaginably vast cosmos. This blurring of cosmic ledgers leads us to an even wilder frontier: chaos-inspired gravity. If the universe isn't a perfectly balanced equation but a dynamic, turbulent system, then galactic rotations might reflect not hidden matter or energy leaks, but the fingerprints of primordial chaos. Picture a spinning coin wobbling before it falls. At first, its motion seems predictable, but tiny, imperceptible nudges send it veering off course. Similarly, galaxies might carry echoes of the Big Bang's initial turbulence, their rotations shaped by randomness frozen into the cosmos's bones. Some models treat gravity as an emergent property of chaotic quantum interactions, where probabilities replace certainties, and dark matter's effects arise from the universe's innate unpredictability. The line between order and chaos blurs, and the answers to galactic motion might lie not in missing mass but in the universe's first, fleeting moments of beautiful disorder. What if gravity isn't the steady, predictable force we've always assumed, but a churning, turbulent sea of chaos? The 21st theory dares to reimagine gravity as a storm rather than a calm current, where random fluctuations could sculpt galaxies in ways that mimic dark matter's grip. Picture a river after a heavy rain, its surface roiling with unpredictable eddies and whirlpools. Now imagine spacetime itself behaving like that river, with gravity's strength ebbing and flowing in chaotic waves. Stars orbiting a galaxy wouldn't just feel a smooth pull toward the center. They'd be buffeted by invisible turbulence, their paths subtly altered by the universe's hidden storms. Over billions of years, these fluctuations could nudge stars into faster orbits, creating the illusion of extra mass where there's only chaos. The math behind this idea borrows from fluid dynamics, where turbulence defies simple prediction. Just as air currents can suddenly shift from a breeze to a gale, gravitational fields might harbor pockets of instability, regions where spacetime's curvature wobbles unpredictably. Some models suggest these fluctuations could arise from quantum foam, the frothy turbulence of virtual particles bubbling up from the vacuum. Others point to the cosmic web's vast filaments, where galaxies cluster like beads on a string. The gravitational tug-of-war between these structures might generate ripples in spacetime, like ocean waves colliding to form rogue swells. If true, then a galaxy's rotation curve could be less a ledger of mass and more a record of gravity's hidden turbulence. Critics argue that chaos alone can't explain the precision of galactic motions after all. Randomness should scatter stars unpredictably, not produce smooth, stable orbits. Yet supporters counter that chaos has its own strange order. Think of Jupiter's Great Red Spot, a storm twice Earth's size that's raged for centuries, held in place by the planet's turbulent atmosphere. Similarly, gravitational chaos might settle into large-scale patterns, sculpting galaxies into the shapes we observe. It's a dizzying thought. The universe's most majestic structures might be carved not by invisible matter, but by the invisible fingerprints of chaos itself. This turbulent vision of gravity leads us to an even stranger possibility: antimatter's hidden role. If chaotic fields can mimic dark matter's effects, could antimatter be doing the same? Conventional physics treats antimatter as gravity's mirror. It should fall just like ordinary matter. But what if it doesn't? Some theories suggest antimatter might repel gravity, creating a kind of negative gravitational shadow. Imagine a galaxy with pockets of antimatter hidden in its halo. Their repulsive push could counterbalance the inward tug of visible matter, stabilizing orbits without dark matter's help. It's a cosmic balancing act where the universe's most elusive substances, chaos and antimatter, dance in the dark, twisting gravity into shapes we're only beginning to trace. The line between order and chaos blurs, and the answers to galactic motion might lie not in missing mass, but in the universe's restless, stormy heart. And if gravity can be this unpredictable, what other cosmic rules might be waiting to unravel? What if antimatter, the universe's elusive mirror to ordinary matter, doesn't just annihilate on contact but repels gravity itself? This isn't just a sci-fi twist. It's the audacious premise behind antimatter-gravity asymmetry, a theory that could flip our understanding of galactic motion on its head. Picture a universe where every particle of matter has an antimatter twin with identical mass but opposite charge. When they meet, they vanish in a flash of energy, but here's the catch. We've always assumed gravity treats them the same, pulling both toward Earth with equal force. What if it doesn't? If antimatter falls up instead of down, galaxies could harbor invisible reservoirs of it, their repulsive push counterbalancing the need for dark matter's pull. Stars on the outer edges wouldn't need extra mass to stay in orbit. They'd be riding a cosmic seesaw, tugged inward by visible matter and nudged outward by antimatter's anti-gravity. The implications are staggering. Antimatter's gravity defiance could explain not just galaxy rotation curves, but the universe's very structure. Vast clouds of antimatter, undetectable because they emit no light, might lurk in galactic halos, their gravitational shadows perfectly offsetting the observed motion of stars. It's like discovering that every galaxy is surrounded by invisible trampolines, gently bouncing stars into faster orbits. Even more tantalizing, this could solve one of cosmology's greatest mysteries. why the universe seems to have almost no antimatter left after the Big Bang. If antimatter repels gravity, it might have been flung to the cosmic outskirts, exiled to the voids between galaxies where we'd never think to look. But how do you test something so radical? Enter the Alpha experiment at CERN, where scientists are trapping antihydrogen atoms, antimatter's simplest form, in magnetic bottles to watch how they fall. In 2023, preliminary results suggested antimatter does behave like ordinary matter under gravity, but the measurements were achingly precise, and the debate is far from settled. Other teams are designing space-based experiments, like the proposed for example is mission, which would launch antimatter into Earth's orbit to measure its free fall in microgravity. The stakes couldn't be higher. If antimatter does repel, it wouldn't just rewrite physics textbooks, it would force us to rethink the universe's scaffolding. Critics argue that antimatter's gravitational behavior should mirror matter's, as Einstein's equivalence principle insists. Yet supporters counter that quantum field theory allows for subtle asymmetries. Tiny cracks in physics mirror where antimatter might slip through differently. And if it does, the consequences would ripple beyond galaxies. Black holes, neutron stars, even the expansion of the cosmos might need revisiting. The line between matter and antimatter could blur into something far stranger, a duality where gravity itself becomes a matter of perspective. This quantum cosmic dance leads us to the final frontier, theories that don't just tweak gravity or invent new particles, but bridge the gap between the infinitesimal and the infinite. Imagine a universe where quantum entanglement, the spooky link between particles across vast distances, somehow influences galactic rotation, or where the vacuum's zero-point energy fluctuates in sync with the cosmos's large-scale structure. The most radical ideas suggest that dark matter isn't a thing at all, but an emergent property of quantum fields stretching across space-time, their collective behavior manifesting as phantom mass. It's as if the universe is whispering its secrets in two languages at once, one of galaxies and gravity, the other of particles and probabilities, and we're only now learning to listen. From antimatter's rebellious gravity to the quantum foam's hidden symphony, the hunt for dark matter's truth keeps revealing a cosmos far stranger than we dreamed. And the most thrilling realization, we might not be missing matter at all, just seeing its shadow through the wrong lens. What if the key to dark matter's mystery lies in the chaotic intersection of quantum mechanics and gravity, two forces that have stubbornly refused to reconcile for over a century? Quantum gravity mixtures propose a radical solution. Dark matter might not be a particle or a modified force, but an emergent phenomenon born from the turbulent marriage of these fundamentally incompatible frameworks. Picture gravity as the symphony conductor of the cosmos, waving its baton to keep galaxies in harmonious motion, while quantum mechanics is the jazz musician, spontaneous, unpredictable, and allergic to sheet music. Now imagine their collision creating something entirely new, a cosmic feedback loop where the universe's smallest fluctuations ripple upward to shape its largest structures. Loop quantum gravity, one of the boldest attempts to bridge this divide, suggests spacetime itself might be woven from tiny, discrete loops. Think of it as the universe's fabric being more chainmail than smooth silk. In this pixelated reality, gravity could behave differently at galactic scales, its quantum-grained texture generating effects that mimic dark matter's gravitational pull. Some models show how these loops might form knots in regions of weak gravity, like galaxy outskirts, creating extra spacetime curvature that nudges stars into faster orbits. It's as if the universe has hidden speed bumps woven into its fabric, invisible to telescopes but palpable in the way galaxies spin. But the real magic happens when you consider universe-wide feedback. Imagine the cosmos as an echoing chamber, where quantum vibrations in the vacuum don't just dissipate, they reverberate across space-time, amplifying certain frequencies like sound waves in a cathedral. Over billions of years, these resonances could sculpt galactic rotation curves, with stars responding not just to local gravity, but to the universe's quantum hum. Supporters point to eerie correlations in galaxy distributions, large-scale patterns that seem too precise for random chance, as if cosmic structures are tuning forks vibrating in sync. Critics argue this is speculative at best without experimental proof. Quantum gravity remains a beautiful hypothesis, yet pioneers like Carlo Rovelli counter that dark matter's own invisibility makes alternative explanations equally valid. After all, if we're willing to invent unseen particles, why not unseen quantum geometries? The debate crystallizes a deeper truth. The universe might not play by separate quantum and classical rules, but by a hybrid logic we're only beginning to decipher. This quantum gravitational tango leads us to an even wilder possibility. What if the universe is conscious of itself, not in a mystical sense, but through self-referential feedback loops where gravity's large-scale structure influences quantum behavior, which in turn reshapes gravity, a cosmic Ouroboros eating its own tail? Some theories propose that dark matter's effects could be the universe's way of remembering its quantum origins, with galaxy rotations as fossilized imprints of primordial quantum noise. It's a dizzying thought. The spin of a single star might be the echo of a reality where observation and creation blur, and the cosmos watches itself unfold. What if galaxies don't just obey the universe's rules, they write them as they go? Cosmic feedback mechanisms suggest that spiral arms, star formation, and even dark matter's ghostly influence might emerge from a self-regulating dance where galaxies sculpt their own destinies through vast, looping cycles of cause and effect. Picture a forest ecosystem. Trees don't grow in isolation. They shape their environment, releasing oxygen, cooling the air, and even seeding clouds that bring rain back to nourish them. Galaxies might operate the same way: stellar winds, supernova explosions, and magnetic fields cascading into feedback loops that fine-tune rotation from the inside out. Take star formation as cosmic regulation in action. When a galaxy's gas clouds collapse into stars, those stars eventually explode, scattering heavy elements and shockwaves that trigger or suppress new star birth. Too many explosions and the galaxy's gas gets blown away, starving future stars. Too few, and rotation stalls under the weight of unused fuel. It's a balancing act where the galaxy itself acts as both architect and inhabitant, calibrating its spin through cycles of creation and destruction. Some simulations show that these feedback loops can reproduce flat rotation curves without dark matter, as turbulence and pressure from stellar activity generate gravitational echoes that mimic invisible mass. But the real magic happens when feedback scales up. Galactic magnetic fields, twisted by rotation into colossal spirals, might channel cosmic rays and gas flows in ways that redistribute angular momentum, like invisible hands gently breaking inner stars while pushing outer ones faster. Even black holes play a role. Supermassive ones at galactic centers can flicker between dormant and active states, their outbursts heating surrounding gas to millions of degrees, preventing it from cooling and forming stars. This aggressive gardening throttles star formation rates, indirectly stabilizing the galaxy's rotation over eons. Critics argue that feedback alone can't explain the precision of galactic motions, why galaxies as different as tiny dwarfs and sprawling spirals all follow similar rotation patterns. Yet supporters counter that we've underestimated the universe's talent for self-organization. After all, termites build cathedrals without blueprints, why couldn't galaxies, given billions of years, find their own equilibrium? This vision of self-tuning galaxies leads us to the edge of speculation where feedback loops might not be confined to matter and energy, but woven into space-time itself. Imagine gravity as a living network, adjusting its strength based on the universe's evolving structure, or quantum fluctuations resonating across cosmic voids to nudge galaxy spins in unison. The most radical theories suggest that dark matter's signature could be the universe's way of remembering these feedback cycles, like grooves worn into a record by the needle of time. From star factories to space-time symphonies, the answer to galactic rotation might not lie in a single force or particle, but in the universe's uncanny ability to compose its own music, one feedback loop at a time. What if gravity itself bends to the will of consciousness not as a metaphor, but as a fundamental law of reality? This is the provocative core of consciousness-induced gravity, a theory so controversial it straddles the line between physics and philosophy. Imagine a universe where the act of observation doesn't just measure gravity but actively shapes it, where the collective focus of sentient beings could subtly warp space-time like fingers pressing into clay. The roots of this idea stretch back to quantum mechanics' most mind-bending paradox, the observer effect, where particles seem to choose their behavior only when measured. Scale this up to cosmic proportions, and you get a radical proposition that galaxies rotate the way they do because consciousness, in some form, has whispered to the fabric of reality. The math behind this is speculative at best, but some theorists point to anomalies like the placebo gravity effect in certain lab experiments, where expectations of gravitational shifts seem to produce minuscule but measurable changes in particle behavior. Others draw parallels with panpsychism, the ancient belief that consciousness is a universal property of matter. In this view, stars and galaxies might possess a rudimentary form of awareness, their collective attention stabilizing orbits in ways that mimic dark matter's pull. Picture a school of fish moving as one, not by following a leader but through an emergent, distributed intelligence. Could galaxies, too, be self-organizing systems where consciousness and gravity are two sides of the same coin? Mainstream physics dismisses this as pseudoscience, and for good reason. There's no known mechanism for consciousness to influence gravity, and the theory risks veering into magical thinking. Yet its supporters argue that dark matter's own invisibility leaves room for radical alternatives. After all, if we're willing to accept unseen particles, why not unseen dimensions of mind? The debate crystallizes a deeper tension in cosmology. How much of our struggle to explain the universe stems from missing data, and how much from the limits of our own perception? This brings us to the final, most humbling theory of all, the possibility that dark matter isn't a substance or a force, but a cosmic blind spot, a gap in our understanding so profound we haven't even framed the right question yet. Like ancient astronomers insisting the stars revolved around Earth, we might be trapped in a paradigm that distorts the truth. The real answer could lie not in the theories we've explored, but in the ones we've never dared to imagine. From quantum foam to fractal universes, from antimatter's rebellion to consciousness itself, the hunt for dark matter's truth has taken us to the edge of science and beyond. Each theory, no matter how unconventional, is a testament to human curiosity's boundless reach. And that, perhaps, is the greatest discovery of all. The universe refuses to be simple, and the journey to understand it is far from over. What if our galaxy's strange rotation isn't driven by dark matter, but by the gravitational whispers of unseen universes brushing against our own? Multiverse leakage is the most audacious theory yet, proposing that the extra force tugging at stars could be gravity seeping through from parallel realities. Picture our universe as one sheet in a cosmic stack of newspapers, each with its own galaxies, stars, and laws. Normally, these layers don't interact, but if they're close enough, gravity might bleed through, warping spacetime in ways we mistake for invisible mass. It's a concept ripped from science fiction, yet some versions of string theory and quantum mechanics actually leave room for it. The math behind this idea hinges on brains short for membranes, a theoretical constructs from string theory where our entire universe could be a three-dimensional surface floating in a higher dimensional space. If another brain universe drifted near ours, even slightly, its gravity could subtly distort our galaxy's rotation, like a magnet pulling on iron filings through a sheet of paper. Some models even suggest that dark matter's halo effect around galaxies might be the imprint of a neighboring universe's mass, forever hidden from our telescopes but palpable in its gravitational echo. Imagine two ships sailing on parallel oceans, close enough that one's wake rocks the other, except the oceans are realities, and the wake is gravity itself. Critics argue this is untestable by definition. If other universes are forever beyond our reach, how could we prove their influence? Yet supporters counter with eerie anomalies. Certain patterns in the cosmic microwave background, the afterglow of the Big Bang, show odd asymmetries that some theorists link to multiverse collisions. Even more tantalizing, if gravity does leak between universes, it might carry faint imprints of their physics, like cosmic messages in a bottle. Future gravitational wave detectors, sensitive enough to pick up space-time ripples from the universe's first seconds, might catch whispers of these extraterrestrial extra-universal tugs. The sci-fi allure is undeniable. Multiverse leakage turns dark matter from a missing puzzle piece into a window onto realities beyond our own. But beneath the spectacle lies a profound question. If gravity isn't confined to our universe, what other forces might be bleeding through? Could light or even time flow between brains? The answer might rewrite not just galactic dynamics, but the very borders of existence. And with that, we've journeyed through 26 daring alternatives to dark matter, each a testament to humanity's refusal to accept cosmic mysteries at face value. From modified gravity to quantum foam, from antimatter's rebellion to the holographic edge of reality, one truth emerges: the universe is stranger than we dreamed, and the hunt for answers is far from over. From modified gravity to cosmic consciousness, from quantum foam to parallel universes, we've journeyed through 26 breathtaking alternatives to dark matter, each one a testament to human ingenuity's refusal to accept the universe at face value. Whether it's meant elegant tweaks to Newton's laws, emergent gravity's quantum entanglement tango, or the fractal universe's recursive beauty, these theories don't just challenge the dark matter dogma, they ignite a revolution in how we perceive reality itself. Some ideas, like antimatter's gravitational rebellion or the holographic principle's cosmic projection, flirt with the edges of science fiction. Others, like plasma cosmology's electrified galaxies or void-based explanations' cosmic deserts, ground the mystery in the physics we know, just viewed through a radically different lens. What unites them all is their audacity. They refuse to accept that 85% of the universe's matter must be invisible simply because our equations demand it. Instead, they ask, what if we're missing something deeper? Some theories may crumble under scrutiny, while others could reshape cosmology forever. But their true power lies in the questions they force us to confront about gravity's nature, spacetime's fabric, and whether the cosmos operates by rules we've yet to imagine. This isn't just academic curiosity. Every failed dark matter detector, every galactic anomaly that defies prediction, chips away at the mainstream narrative, leaving room for these wild alternatives to flourish. The history of science is littered with discarded certainties, phlogiston, the ether, even Newton's absolute time, reminding us that today's orthodoxy could be tomorrow's footnote. Whether dark matter falls into that category remains to be seen, but the sheer creativity of these challenges proves science is alive, messy, and gloriously unpredictable. So where does that leave us in the golden age of cosmic mystery, where every unanswered question is an invitation to explore? Maybe the answer lies in one of these 26 theories. Maybe it's waiting in the gaps between them, or in an idea so radical no one's dared speak it aloud yet. That's the thrill of the hunt. The universe loves a good plot twist. Your turn now. Which of these theories electrified your curiosity? Dive into the comments and champion your favorite, or invent one of your own. And if you're hungry for more mind-bending cosmic mysteries, hit subscribe. The universe has endless secrets left to spill, and we're just getting started.